Now that we have that working, I actually do want to go back to our animation system and I want to explain this formula a little bit more. So here we have the current frame formula. How does this work? Well, I can give you a very brief explanation. I'll go through each one of the properties one by one. To start off with, we have game time. And game time is the time in milliseconds that the game has been running in. And the reason we start off with that is because we want to know how long we've actually been running this animation for, which is then why we subtract current time of animation from the game time, because this difference tells us how long the animation has been going on for. So now that we have the total amount of time that has elapsed since we started, right here, we'll multiply by the animation frame speed rate, so the number of frames that we want per second. And since we're working in milliseconds, we need to divide it by 1000. The trick now is to know which of the frames we currently are in. And this is where the final part of this equation comes in, using the modulus operator. The modulus ensures that we always have a remainder that is between 0 and the number of frames that we currently have in our property of num frames. And the math floor function just keeps this as a simple integer and gets rid of any long decimals. So now that we've completed that, and we have Link properly animating himself on the screen, now we want to get into something fun. Let's start rendering our world in the first few screens of the game. In our game, we're going to map out how each one of the screens that Link can walk onto, how each one of the tiles of the map looks. So I'm going to show you how we do this. We're going to do two main things. One, we're going to create our first screen. And two, we're going to go into index.js and teach our game class how to render each screen. So to start, we'll go and we'll create a new screen. And we'll put this new screen in its own folder. We'll just call the screen.js to start. Now, if we go and look at the Legend of Zelda, how the video game looks, we can see from screenshots just on Google that since it's a two-dimensional game, we'll render it by its x-axis and then its y-axis as well. So there's going to be rows and columns of tiles that we need to tell our game to render on screen and then to perform certain actions. With this in mind, we need to know how many columns across and how many rows down we need to render to make our game look like the Nintendo game. I've already went ahead and done this research for us. I know that we need to render this by 16 columns and 11 rows, and we're also going to have a few extra columns and rows as padding to handle off-screen interactions. So when Link runs off-screen, we want a transition to occur to the next screen that he's running onto. So with this in mind, let's go back. And we're going to create our first screen. And I'm going to make it an object. So we can call this opening screen, because this is the first screen that appears in the game. And this is going to be a complex object as well. There's going to be many properties, and the properties within this object may have properties themselves. The first property that we're going to have within opening screen is going to be called screen. Not very creative, I know, but it illustrates what it is that it will be doing, the kind of information that it will contain. Now this screen is going to be responsible for rendering the specific tiles that we want to display. And the way we do that is by having an array. And this array is going to have arrays within it as well. And for each row, we're going to have an additional array. So since we want to have 13 rows and 18 columns, we're going to have 13 arrays in this array. 3, 6, 9, 12, 13. And each one of these arrays is going to have 18 values within it. And what are these values going to be? Well, they're going to be different data types. They're going to be strings, numbers, and undefined, and also objects a little later. And we're going to write into our index.js how to translate the types of data that we're putting into our screen array. So the first thing that we're going to do, we're going to create an undefined type. This is going to be padding around our screen. And this padding is essential for handling transitions, and we're going to see that a little bit later. But for right now, I'm going to pad our screen with these undefined values. So the first top row is going to be completely out of bounds. So it's going to be filled up with undefines. So that's going to be 18 O's that will be in this array. That's 18. Just going to put this in the bottom as well. Now that we have the padding of the top and bottom of our screen, we need to put the padding on the left and the right side. So we need to have the first value within each one of these arrays to be O, and the last value. Let's just copy and paste that. And don't worry, we will be filling in these open spaces very soon. Now, if we go into our assets and we go into Overworld, I've laid out a few different folders that have different kinds of tiles within them. Go into Tiles, and you can see that the first tile that we have is 0 PNG. Now first, let's just render our world with this tile, and we're going to just use this tile for every space to begin. So I'm going to select all of these open spaces. Set them all to 0. So we will have just an open screen only using this tile. Now that we have this, let's go into our index.js and let's render this blank screen. To do this, we're going to create 2 new properties as well as a new function within the game class. This game class is going to denote how many rows we have, and then the second property is going to denote how many classes we have, or excuse me, how many columns we have. So this num rows, we have 13 rows including the padding space that we put down, and then we have 18 columns including the sides of empty padding space that we have. And let's create this load screen method. And the argument that it's going to take, it's going to take this screen object and what we're going to do is we're going to be looping through opening screen property, and based on what the value is that we find in here, we're going to render the specific tile that this belongs to. So it's 0 PNG. We're going to take 0 and say, oh, okay, 0 PNG must correspond to 0, and then we will render it. We're also going to keep track of the number of tiles so we can assign it the proper ID. So for let I is equal to, we can begin with rows first, So we're going to go through each row. Now this is going to go down through the rows, but we also want to go through the columns as well. We want to go through each value within every row. So we need 2 for loops here. And we want to determine which tile it is. Later we're going to be adding different data types to this. So we're going to have strings in here, for example. We're going to have a string that says 0. We might have a string that says 1, 2, 3, 4. So we'll create a logic statement that determines what type it is. Let's get the tile. Screen object, screen, the type of the tile is equal to number. Then we will go into this tiles to find which specific PNG we want to use. So the type is just determining what folder we're going into. And to hold this value, I'm going to actually create a variable to hold it. And now let's actually create a sprite dummy component for this. And what does this take? Well, remember, if we go to our sprite component here, it's going to take the path, which is path plus tile, because the tile is the name. Tile looks like 0. And then it's also going to take the file ending as well. So it's going to look something like this. Tiles 0.png. We also need to be able to navigate to the folder, so I actually am missing one part. It's going to be tiles. And since this is the full path, but since we're going to have multiple screens and not every single one is going to be within the overworld, what I do want to do is I want to go back to our screen and I want to put a property called asset path here. And what I want to do is I just want to take this, put it in here so that way it's unique to the specific screen. And then I'm going to pull this value from asset path as well. So now that we have our sprite dummy component, what are the other things that we need to make it render? Well, let's check our render system. We need a position as well. So how do we get the position? The X and Y values of the tile determine where it will be on our screen. So all we need to do, realistically, is we need to get the I and the J values from our for loop and use those as our X and our Y position in a dummy position component. We call this dummy sprite. That's dummy position component. So X is J, because J is related to the columns. Y is I. However, it's not just this. We need to space out each tile by the width that we want to have for our game. The width of each tile we want to have. So we need to think about how big it is that we want to make our video game. This can be an arbitrary value that you choose, but if you want to follow along closely with me, I suggest you choose the same value. Now, I personally decided just to make the tile width to be 70. And actually, to make sure we never make a mistake with this value, let's actually just create a constant. Replace those 70s with that value. And now let's create our entity using the registry. Registry, create entity, dummy sprite, dummy position. And finally, let's test this and make sure that it worked properly. So I'm going to export, opening screen, and upon initialization, let's load up the screen. Let's add the type of tile equal to undefined. And if it's undefined, we can just continue. Now that we have this function set up in the create entity, so how we're handling adding entities to the system is we're actually doing it right here. And I did this before just as a demonstration. However, how we're going to handle this, so we're going to delete this. Actually, we can keep that. So we're setting the displayer value for the game from here. But what we're going to do is we're actually going to take this line, we're going to comment it out. Good. Now that we have the entities to be added, we have an array, and this array of entities to be added is being filled up by this function right here. So we're going to have, I don't know, 100 something entities of tiles. However, it's not added to the system. It's only in the create entity function that we have this value, right? Or at least that this value is being interacted with. That's how I should say it. It's just being interacted with in this function. We want to get these entities into the render system. So how do we do this? Well, we have this add entity to system. That's great. But we need to call this on every update. So before we were using this function directly in the initialization function of the game. Now we want to call this upon every update. So what we're actually going to do is the registry is going to have its own update function that runs, and it's going to handle a few things. One of those things is it's going to check this array, and if there are entities in it, well, or for each entity, it's going to be added to the system. So this add entity to system entity. And then let's call this update function in the index.js. And a side note too, as an architecture decision, you can see here that we're calling this update, and theoretically we could put these updates for each system inside the registry update function, But I decided to not do that because as we go along and we add more systems, you're going to see that these systems will require a lot of parameters for their update function. For example, the animation system, it only has this single argument that needs to be passed, but you're going to see some systems take more than one argument. They might take 3 or 4. To keep it clear, that's why I'm calling these functions here in the game's update function rather than putting them into update. And later, the registry update will handle more than just the entities to be added. It's going to be handling the entities to be removed or the entities that are killed later, along with a few other things. So this update function will serve a definite purpose as we go along. So let's see what we got now on our screen. Seems I have an error. Screen object is not defined. That just means I have one extra E right here. Now let's see. Yes, cannot destructure property X of src as it is undefined. So in the system.js file, I currently have, I'm destructuring this, however, there is no src that's being passed the dummy sprite component. The thing about this PNG is we're going to use the whole entire file. So when we pass in values, we don't actually need to specify the width and the height and the X and the Y of the sprite sheet since we're using the whole thing. And the way that this draw image works is if you don't specify the source and you only pass in 5 arguments, it's going to just take the whole entire sprite sheet. So what I'm going to do, I'm actually going to create src rect, and we'll set it as a let. And I'm going to set it to undefined. And I'm going to pass it in to this object, just like that. Now that it's undefined, let's go to the system that we use it in. And it's undefined here, so what's going to happen is it's still going to throw an error because we're trying to destructure this property, and it can't pull out X from something that's undefined, so it will throw an error. So what we're going to do is we're actually going to just wrap this draw image in an if statement. If src rect, then draw the image. And we're going to take this destructuring and we're going to put it in here because this is the only scope we're going to need it in. The other situation will look like this. We're going to draw the image, and as I said, we're going to be able to use the whole PNG file by not specifying a source X, Y, width, and height. So I just need to pass an X, Y, width, and height, like that. So we're properly rendering every image, or every entity, I should say, that is inside the render system. We're creating the entity, and in this create entity function, we're passing the entity, or we're pushing the entity into this entities to be added array. Now, after this is all done, we don't want to continually add the same entities that were already added, so we need to clear out this array. In JavaScript, we can simply just set this entity to be added to another blank array. So when it's done looping through all the entities that need to be added, we just simply set it to an empty array. It's that easy. And from there, we're going to go to the update function, and we're going to write this registry update just like that. We should probably fix the aspect ratio on index.html. It looked like to me the aspect was a little off, so let's make some CSS changes. And actually, I want to get rid of this because now we are setting the canvas style. We're setting the canvas height and width with JavaScript, so this is actually obsolete. Let's try setting the aspect ratio to something like Maybe 120 by 770. Let's see how that looks. Oh. Not bad. It needs the position to be fixed. Let's set the position to be absolute. And I think I want link to now be the height and the width of the tiles to keep it proportional, minus just a little bit, so maybe like 10-15. Let's see how that looks. Yeah, I think I like that proportion. Right now, link is going behind the tile, but don't worry, we'll fix that in a minute. Yeah, I think that proportion looks good. Very good. Now we're rendering all the things that we need to be rendering. But this kind of map, it's not very fun, right? There's nothing to it. There's no terrain, there's no rocks, no obstacles. So I'm going to take you into the assets folder. And right now I want to go into overworld and then collidables. So if you've not went through these pictures, these are pictures of rocks that are found in the game. And what we're going to do is we're going to render them into our game, and then we're going to make them collidable. So Link is going to have something called the collision component, and so are these tiles. And Link is going to not be able to pass them. We're going to write a system called the collision system that will detect anytime there is any kind of intersection between these or between entities that have a collision component. If there is some kind of intersection, Link will be pushed back. He'll be pushed away from the object. So it'll give the illusion that Link is running into the object. He's colliding against it and bouncing off of it. Very slightly bouncing off of it, but still. To do this, let's go back into our screen, and we're going to add these tiles. So what I want to do before we do that, actually, let's go Link NES Legend of Zelda opening screen. Let's look at this, and we're going to look at how this level is set up. And we want to render this level and the tiles that it contains. So I'm going to put this side by side. And we can build this together. Close out all these things. Let's open up the collidables. And I'm going to put these PNGs on the bottom. This is the edge. This is the middle. This is the other edge. Actually, let's switch places with the 4. So we're going to start from the very top left, and we're going to go row by row. So the first tile looks like it's just this plain 1.png.
So we even programmed the logic in, but anything that's collidable is going to be a string. Because if you remember in the game.js or index.js in the game class, we're determining what the type is to go into. So we're going to go through, we'll add 1 because it looks like it's 5 rocks. And let's use this as an example. Maybe I shouldn't get too ahead of ourselves. Let's go into the index.js, into the load screen function. And let's set this tile path. So type of tile, if it's equal to string, let's do path collidables. And I think that should work. Yeah. We open up our game and we can see that the tile that we want, the PNG that we are trying to render, is successfully rendering. So we're doing something right. Now let's see. That's 5. 1, 2, 3, 4, 5, 6, 7. Maybe that's 6 or 7 actually. And it's cool to use this technique because it may not be a perfect depiction of the screen, but you can kind of look at one of these two-dimensional arrays and you get an idea for the screen and what it's supposed to look like. Cool. Now there's 2 open spots, so we're going to leave these 2 zeros. And then the rest of the zeros should be replaced with string of 1. Okay, let's see. I'm going to zoom out a little bit just to take a better look. That looks good to me. That looks pretty on center. That looks pretty good. We can always make changes as we go. Then the next row is 4 rocks, followed by this door. And we're going to handle the door a little bit differently, but for right now, let's just leave it a blank tile. Let's skip that door. This would be the door, so we're skipping it. We're going to go to this one, blank tile. And now we need to use a corner rock. The corner rock is 2. And now we got the beginning of our game, or how it's supposed to look. We leave 2 open spaces for the pathway. And then we can fill in the rest of these zeros to just be 1s. Easy. And I'm actually going to... No, I'm going to keep doing it from left to right. Let's just do it like that. That's the best way to do this. 1. Ooh. 2. Right? Maybe I'll just put it down here. There we go. That way we don't need to keep changing between tabs. Good. There's a bunch of open spaces. And I think this is where the rocks must be. Yep. This is just 2 1s. Now, it's pretty easy to lose your place, so don't worry. Just follow along with me. Slow down the video if you need to. This is a really cool technique, and it's used by a lot of video games from this era. And this is 3. Yeah, that is 3. And then the rest are 1s. And it's fun because using this technique, you guys can create your own maps if you wanted to. Oh. You can create your own maps, your own screens. Feel free to be creative with this. Once we're done with this video series, if you want to make your own maps or change the Legend of Zelda's map, please go ahead and do that. Leave a comment down below or send me a PNG. I would love to see what you guys make. This one is not a 1. This would be a 5. 4. And then again, it's a lot of open space, with the last 2 being, I think it's 5. Then this is another 1. The last 2 are 1s. Starting from the right this time. 1, 1. I like doing this too, side by side, because as we're making it, we literally see this map come to life. We're going to have an exact replica of this screen from the Nintendo. Very cool. 1. So the last row begins with 2 1s, and then everything is 5 except the last 2 values. And it looks like we're good. We have our first stage, albeit we're missing the door, but we're going to handle that later. Now we want to give the collision property to all of these tiles, and we want to give it to Link as well. So let me exit out of all these images. We're going to go to our index.js. We're going to go to our load screen function. And here, what we're going to do is we're going to create an entity that has this dummy collision component. But since not every single sprite is going to have a collision component, we only want to push into the create entity function the components that we need. So what I'm going to do is I'm going to create an empty array, and I'm going to push into this empty array the components that are created. So components push dummy sprite, components push dummy position, and here we are going to create const dummy collision component, name collision, and this is going to be a slightly special component. All the other components had a value object that they carried specific values in. Now, you can structure your game to have its own X and Y, width and height collision component that is independent of the position. So you've probably played video games before where you may see a character on screen, but perhaps his hitbox doesn't exactly line up to what you see on the screen. That's sometimes by design, and that's sometimes unintentional. In our game, though, since we are going to simply correspond link's collision component and the collidables collision components to the position that the entity has, we actually don't need to create a value property in this dummy collision component. Now, you could easily have done something like this, yada, yada, yada. You guys get the idea. So we're simply going to detect if it's collidable by the existence of the collision component. So we're going to now components push this in. Dummy collision component. And now we're going to remove this and just pass in components. And on screen, let's go through our entities. Or let's just go, we'll open up the player, console.log, this player, this dot player. Just to make sure that it is getting into the player properly. Entity. It is not. It's not because I got ahead of ourselves. We need to actually add it through these registry functions, and I also need to create the collision component itself. So I jumped the gun a bit, but that's okay. Let's just go and create it here. Class collision component. Spelled collision wrong. Extends component. Constructor component type. Now this is only going to have a component type because again there are going to be no values that we associate with the collision component. Let's export it. Now we can import in here. Const component object is equal to component value. Follow the pattern that we've been doing for a while now. Collision component. Now we actually don't even need this. It's going to return undefined, obviously, but it doesn't matter in JavaScript. So just to follow this pattern, you can still call it like that. We need to put the collision component directly into the player because we're handling the player slightly differently at the moment. Name collision. Okay, so the collision component is in the player. We'll just console.log out some of these entities to make sure. It's also getting in here properly too. So very interestingly, you can see also that the IDs have incremented. This is good. We're going to be using this later. Now some don't have the collision component. This one does. There we go. This one is one of these tiles that's just on the ground. This is a walkable tile. We can interact, well, we can walk across this tile. Now what we're going to do is we are going to go to the system file, and now we're going to add our system class, or our collision system class. Collision system extends system. Constructor system type, super system type, and this component requirements is going to be equal to position, because it needs a position, and it needs a collision component. So on update, every update cycle, this system is going to check between the collidables and the player and make sure Link isn't hitting any one of the tiles that has a collision component. So ultimately, we're going to need the player. So we're actually going to take a player argument, which the registry, or the game, I should say, the game is going to pass the player from this function. So it's going to be something like this registry get system collision system update this player. That's what it's going to look like. I'm missing some parentheses there, but that's just for illustration. So once we have the player, we can loop through all of the entities and every entity that has a position and collision component is going to be in the collision system. And that includes Link. Now we're passing in the player, which is also Link. So there's going to be chance for both the player and one of the entities from this for loop to be the same thing. So what we're going to do is we want to compare IDs and make sure that the IDs do not equal each other. If they do equal each other, we're going to just continue because we're going to know that that's the same entity. So if player ID is equal to entity ID, continue. Now that we know that the player ID or the player and the entity are not the same because the IDs aren't the same, now we can compare to make sure that they're not overlapping one another. Now, in order to calculate if two squares are overlapping one another, there's a very popular formula that you can Google or find on Stack Overflow for the overlap of squares. I'm going to write it out for us right now in a logic statement, and it's kind of long, so follow with me. So the first question we want to ask ourselves is the player X less than the entity X plus entity width? And I want to say that it might be a little bit difficult to visualize how this formula actually works. I encourage you at home, if you have a piece of paper, to draw this out on an X and Y axis to see how this actually works. It's not very intuitive, but this is the formula. So then it's player X plus player width is greater than entity X. Then it's player Y less than entity Y plus entity height. Then it's player Y plus player height is greater than entity Y. And what I'm going to do is I'm going to console.log out true if it's true. I'm going to remove this other console.log out, so this is clear. Let's see if we have it working. Currently, we do not have it working. Console.log out entity. Oh, well, we don't have it working because we're not actually calling the system yet. So let's actually export the system. Let's go now to our registry. Case collision system. New system is equal to new collision system. System type. We're going to break here. And then an index.js. Let's add the system. This registry add system. Collision system. And then we will update the system. Can even uncomment this out. Let's see if this is working now. Does not seem to be working. Okay, so it is being called. That's good. Okay, so we are getting the player in here. That is working. I made the mistake of forgetting that we had specific components that had these values. So the components that have this value is the position component. So I need to take out the x, the y, the width, the height of both the player and the entity. So I'm going to do const x, and I'm going to do it like this: x px, y py, width p width, height p height, player dot components dot position. And this will be for the entity now. EX, EY, E width, E height. So PX, EX, E width, if you guys didn't make this mistake, you can just skip ahead in the video. Okay, let's see if that fixed it now. Doesn't seem like it did. Oh, yes, it did. Just took another refresh. And when I enter it, it says true, but when I leave it, it stops incrementing. So we have successfully programmed collision into our game. Fantastic. So now what we want to do is when Link collides with an object, we want to know from what direction he's colliding in, or what axis he's colliding in at least. There's some fancy mathematical formulas that we can use to apply this logic in our game. However, for right now, what I want to do is I simply want to use the current velocity on the x or the y axis to determine in what direction Link was running. And in that direction, we're going to set, or in that axis rather, in that axis, we're going to set a collision value within the movement component to true. If you remember, when we go to movement component, we first coded out these two values. We're going to use these values now, or at least we're going to set them, and then we're going to use them to limit movement in the direction of which Link is running. So once we have collision, we know that he's colliding. What we're going to do now is get the movement component from the player. And if movement Vx is not equal to 0, and there was a collision, then we know that the collision must be on the x-axis. The same goes for the y-axis as well, and the y velocity. Seems we have an extra There we go. And now what we're going to do is we're going to use these collision properties in the movement system to prevent Link from moving forward. And now that we have this, what I actually want to do is I'm going to move this up here because I want to include the movement's velocity into this equation, because if you think about it, we're only going to detect Link when he's in the square. So it's going to be a little too late to keep him from actually being inside the object. But what I want to do is, since it's just a very small distance, we can actually incorporate the movement in here. And this is going to predict before he's actually inside the square. I'm destructuring it from movement itself. Although I could actually just do that. X, V, Y. Actually, no, we won't do that. JavaScript only passes by reference objects, not primitive type values. So we actually need to pass this as an object right here. So here. Okay, very good. Now what we're going to do, let's go up to the movement system, and we're going to add these collision values in. So I'm going to pass this collision component in. So not every entity that is in this system has the collision component. As you see, it's only guaranteed to have the movement and the position components. So let's just wrap this in an if statement. And let's write a little logic. So if collision X, so if that's equal to true, then we want to set this entity or this movement Vx equal to 0. And we want to actually reset this entity. We want to reset his position a bit. But real quick, let's just see if this works. We actually need this to be movement. It's not in the collision component that the collision exists. It's within movement. Awesome. So Link is colliding to the right. I mean, now I can't move Link, but the collision is detecting. And what we want to do now is we actually want to push Link back very slightly so that way it will no longer be overlapping. And we do this by determining what direction Link was facing when he made this collision. So if, and we got to get the facing now, the facing property. And if we remember, facing is within the animation component. So we can go in here. So const facing animation. If facing right, we can take the position X and we can minus it by, let's just say 2. If facing left, position X plus 2. Let's do that for Y now. And actually, I'll just put this up here because we'll be using facing as well. For Y, if movement collision Y, movement Vy is equal to 0 if facing up, position y is going to be minus, or no, it will be plus actually. And then for down, it will be the inverse of that. And then also after this is all said and done, we want to set the collision to false because we have fixed it after applying this. So let's see. Oh, facing is not defined. There we go. See that? Now Link is bouncing off this rock. So what I'm going to do is refresh this. Open up this map. Link can't enter here. We'll have Link run around the rocks, slow as that may be. Now, he is going behind the screen. We'll fix that. But you can see he can't go down. He can't go up. He can't go right. And I hope he can't go left either. We'll make sure he can't in a second. But it looks pretty good so far. I like how this is looking. Let's scroll down. And in the render system, you're going to go into this if-else statement. And here, that problem we had before with the link being under the map, the context object handles layering a little weird in JavaScript. Now, there is a property that we are going to set within the context that is going to determine how the layering of the tiles are going to work. So this property is called global composite operation. And there's a multitude of values you can pass into it. The two values we're going to pass is source over for link. And link is rendered within this if statement because he has a source rectangle because we're taking him from a massive sprite sheet with other sprites. And we're going to copy this line, paste it in here, and then we're going to write destination over. So these are two strings that the context recognizes to determine how the layering is going to work. And it's self-explanatory in the actual parameter that you pass in. Source over means whatever you are taking to put onto the screen, that will be the thing that's on top. While destination over means anything that's already on the screen is over what you're putting onto it. So let's say you have a link and then the game wants to put a tile exactly where link is. Destination over says whatever is at the destination already is the thing that will be on top. Okay? And source over, is, as I just explained, is the inverse. Whatever is already there will not be on top with source over. It's whatever I'm putting down. So we're basically saying to the game that link will always be over the background tiles. Hope that makes sense. I'm going to run over the tiles and we're going to see that it's actually properly working. Look, link can run. Our left collision works as well too. Let's put link into the middle of the screen so I don't need to continually run around. For position, let's just do, and I don't know if this is the right position, but we'll just do 2 500s for X and Y. That looks, wow, that looks pretty much perfect, almost identical to where he starts off in the game. Cool. That looks good. And actually for speed, why don't we just make link a little quicker for the sake of testing. We'll make him 5. We'll make him 5, and then he can run very quick. Yeah, there we go. Oh, seems like there's a little bit of a bug with up, though. the collision sticks. I think what we need to do is just move this out. Since we have it at 5, let's add the pushback to be 6. Because if Link is faster than the pushback, he may actually be able to clip through the collidables. It'll be a rare glitch, but that could still occur. So let's try it again. Very nice. Oh. There we go. Huh. The hitbox for the rocks is pretty big now that we included such a large amount of speed, because the speed is taken into context to push Link away and keep him away. For debugging purposes, though, we can keep it like this. Speaking of which, when I start programming video games, I like to have a debug system in order to help me figure out what is actually going on to illustrate better things like hitboxes. So what I'm going to do now, and this is a really important part of video game development, let's program a very small, effective debug system just to help us determine where the hitboxes are for these rocks, for the collidables in general. Let's go back, and we can start just by going into this player input function. And for this player input function, we're going to want to have a Boolean flag we can switch on and off, a button that we can press to just pull up some debugging information. And we're going to program out this debugging information very shortly. But we'll start here, and I'm going to use the letter G as my debugging button. And we're going to create a property called isDebug. We're going to just flip it on and off based on G. I'm going to add it up here. This isDebug is set. And we're going to start it off with true to begin. And the debugging system I have in mind is we're going to draw just a red rectangle or red outline around each collidable to determine where the hitbox is. So we're going to be altering the render system. Let's pass in this isDebug into the render system update function. And let's go to the render system and isDebug. We'll add that as an argument. And now we'll write if isDebug. So if the debug setting is set to true, if collision, so I can actually just pull it from right here, collision. If collision, do something. And what are we doing? We're going to draw a red rectangle, or red outline rather, around this entity. So context uses something called rect, and you pass in its position parameters. You set a line width. You could set that to 2. The stroke style now, stroke style, we could set that to red. And now let's see what we got. We have our red rectangles. And if I press G, it turns it on and off. Okay, very cool. This is going to be very useful for us to figure out where exactly Link can and will collide